Welcome back, Matadors. After a couple of days of labs, the virtual lab as well as the previous video in which I showed you convex and concave lenses and exploring what we can see through those, we're now going to read about why they work and how they work and what you should have seen in both your virtual lab and the physical lab or video that we saw previously. So lenses, such as binoculars, eyeglasses, even your eyes, and cameras, they all contain lenses. What is a lens? A lens is a transparent object with at least one curved side that causes light to change direction. Recall that most of the light that strikes a transparent material passes through it. Light refracts or bends as it passes through a lens. The greater the curve of the lens, the more the light refracts. The direction of refraction depends on whether the lens is curved outward or inward, which we kind of talked about in the last lesson. In the figure below, light beams pass through two different lenses from the right. A lens that is thicker in the middle than at the edges is a convex lens. See, it's thicker in the middle than on the edges. It's a convex lens. Notice that the light rays that move through a convex lens, now they're coming in from the right. The light rays that move through a convex lens then come together, or the word is converge. Converge, meaning coming together. Now a lens that is thicker at the edges than in the middle is called a concave lens. It's kind of caving in here. And notice that the light rays, once they go through, they spread apart. Or the word is diverge, or coming away from each other as they move through the concave lens. So these are the two different lenses that we looked at. The convex, where they converge as they go through, and the concave, where they spread out, the light rays spread out as it goes through. So let's look more deeply into each of these. So a convex lens, the refraction of light by a convex lens is shown in the figure to the right. Now notice that the normal to the curved surface slants toward the optic axis. Okay, so remember the normal is the straight across and the optic axis is like in the middle. Recall that light moving into a slower medium turns toward the normal. We talked about that in the previous reading. As a result, the convex lens refracts light inward and converges. So everywhere it's going to go through the glass and it's going to bend toward the normal. Now the normal is going to be right here, so they're all going to be bending towards that, coming to a focal point. So convex means to converge. Convex, converge. Then we have a concave lens where it's caved in the middle. Light rays that pass through a concave lens diverge or spread apart. The figure at the bottom right here, shows why. Now notice that the normal to the curved surface actually slants away. Right here in the middle, it's going to slant away. So from the optical axis. A line perpendicular to the center of the lens is the optic. So this is the optic axis, just a reminder, the optic axis. And because light entering a slower medium changes direction toward the normal, the lens refracts light outward or diverges. So concave lenses diverge the light or spreads it out. Okay. We're going to skip this one and I will do this one with the lesson review tomorrow. So I'm going to move on to page 118, moving on to focal point and focal length. Similar to a mirror, the point where rays parallel to the optic axis converge after passing through a lens is called the focal point. Now, we talked about focal point and F in our virtual lab. You should have seen this in your virtual lab. If you haven't done the virtual lab, I suggest you get it done this week. It's very interesting. You'll see focal length and 2 times the focal length, and you'll get to move objects around in that online and see what happens as you move it to and from the lens. The distance along the optic axis between the lens and the focal point is called the focal length. Now, because you can look through a lens from either side, you can look at it from this side or from this side, a focal point is on both sides of the lens. So there's one on this side and there's also one on this side. For the lens with the same curve on both sides, the lens's two focal points are the same distance from it. And that you did see that in the virtual lab where it was on both sides. Types of images, and I did give you some information about this so that you could do your virtual lab, because different types of images it's a little confusing. So, like a concave mirror, the type of image that a convex lens forms depends on the location of the object. So there's a convex and a concave. Now, in a convex lens, which is this one up here, they can actually form both real and virtual images. Real and virtual images with that type of lens. And the diagram shows only two rays, but remember, in reality, there's an infinite number of rays when it's light rays because they're coming in from all sides. Now, if you look through a magnifying lens at an object that's more than one focal length from the lens, the image you see is inverted and smaller. And you did see that. We did see that inverted or upside down image, and it was smaller when it was more than a focal length. If you look at an object less than one focal length from the lens, the image you see is now upright, flip upright, and it's actually larger. Hence magnifying glass. It will magnify and it will make the image much larger. Now the image is virtual, this larger image, it's not real, but your brain thinks it's real, and that's why it makes it virtual. Your brain interprets the rays as moving in a straight line, so they're like actually getting bigger. So to your brain and your eye, the image appears bigger. That's why it's virtual. Okay, let's move to our 3D thinking section. Starlight out in space comes from so far away that it comes to Earth in parallel waves. Please make a model of this light and a lens that you could use to collect light. Now, if there's a lot of rays coming in, we want something that's going to focus all that light in. So that's where you want to have a convex lens to gather all that light that's coming in at parallel rays. You make your rays a little bit more parallel. Mine aren't that good at being parallel. And it kind of takes all that light and it focuses it. And then I made this more look like a telescope. You can make yours smaller, it's fine. And then at the end, we don't want just this, all the light focused in on one spot. Your brain won't be able to interpret that. So we need to spread it out again so that you can actually see what it is that you're looking at. So we need a concave lens to spread out the light again in order for you to see that image. So we need a combination of a convex and a concave lens in order to see out into space. Okay, and you're welcome to look this up as well, like what a telescope, what types of lenses are in a telescope. The last thing we're going to do is we're going to go over to our CER and add some more evidence on page 109. So let me flip over to 109 here. And evidence B. What evidence have you discovered to explain how lenses affect the way an image is seen? So I helped you out a little bit here. We've got convex lenses. We need to add that. They make real and virtual images. Okay. Now, how do they do this? I want you to tell me how a convex lens works. Okay. If you need to go back to your notes, please do that. The other thing we need to add to our evidence is a concave lenses. They can only make virtual images. Why is that? What are they doing with the light that only makes virtual images? Okay. And then you can go ahead, now that you've gathered all your evidence, you can revise your claim from over here and revise it now to answer why you think the polar bear's body looks different in the water, now that we have a lot more information about light and how it's moving through mediums and different lenses. And then you can back that up with evidence from what we've learned. Make sure you're doing 3 to 5 complete sentences, please. Okay, by the end of 8th grade, you should be able to write complete sentences. And at least 3 to 5 of them. There's a lot of information in this unit. Okay, tomorrow we'll get to our lesson review.